A pretty classic example of projectile motion is launching a bottle rocket off the top of a building. So let's say we want to launch a bottle rocket. We want to launch it off the top of the building, and we can start its initial velocity at 20 meters per second. We're going to launch it at an angle of 35 degrees above the horizon. And we want to calculate the height of that building if the rocket hits the ground 2.8 seconds after. And this is actually an experiment you can try, you can calculate. You can set your certain parameters, you can set your measurement based off the amount of acceleration or propulsion. You can calculate the initial velocity of the rocket launch, and you can time it to see how long it takes to hit the ground, and you can figure out certain variables. If you knew the height of the building, you could calculate the angle degree of launch. If you didn't know the height of the building, like this problem, if by measuring out the angle of launch, you can calculate the height, and a bunch of other varying components and things like that. And so this is a really fun problem to do because it kind of really is a good example of parabolic motion. Essentially, it's a two-dimensional problem, and the best way to solve two-dimensional problems is to break them down into two one-dimensional problems. And for this one, it's really nice for this problem particularly because we're not really looking for anything in the x direction. We don't care how far away from the building it went, though we could calculate that. We just care about the height of the building. And once the rocket leaves whatever it's being launched off of, there's no acceleration in the x direction. The only acceleration acting on the rocket is gravity, and that's all in the y direction. So for this problem, so long as we just break down all the y components, that's actually all we care about. There's not really much fun going on in the x direction. So let's break it down. Let's look at the y components, and we're going to start by looking at the velocity specifically in the y direction, because that velocity is given to us as is in both of the directions, right? It's at a diagonal. We just care about the y component of that velocity. So here's that angle, we'll call it theta, and this is the total velocity. What we care about is Vy, and Vy is the total velocity times that sine of that angle of elevation that it's repulsed off of. And when we plug velocity into the kinematic equations, this is the velocity we are going to use. Now that we have our velocity component, the way I like to set up this problem is I'm going to break it down into two different timestamps. I want to look at the change in time as the rocket is going up, and I want to look at the change in time as the rocket is going down. And the reason I want to do this is because when you think about the parabolic motion, as the rocket is going up, so it's going to start here, it's going to go up, it's going to have a parabolic arch where it's going to reach a specific height, and then it's going to go down, right? And it's this peak, this arch, that I care about. If I am just thinking about the motion in the y direction, that basically says that the rocket is going to go up, 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 and eventually it's going to stop, and then turn around and go down. And it's that stop part that I care about because that tells me my velocity is slowing down until it becomes 0, and then it turns around and changes direction. So I have an initial velocity in the y direction, and I have my final velocity being 0. And this helps me a lot because I then also know my acceleration. If I use actually just the equation for acceleration, acceleration is equal to the change in velocity over the change in time. I can use this to calculate the change in time. So if I just reorient it to the change in time, this want to be specific. This is the change in time it takes my rocket to go up before it starts coming down, okay? And that is equal to the change in velocity in the y direction over the acceleration, which is, the acceleration in the y direction is gravity. It's just gravity. And so using this, I can calculate what specifically that is, especially considering it's going from that change in the y direction, right, we just stated, so it's the final minus the initial. The final velocity is 0, because, right, it stops. So it's 0 minus the initial velocity, the Vy component that we were calculating from the launch. And that's going to be all divided by gravity, which is negative 9.8 meters per second. So we'll have gravity right here. So to calculate the total change in time of the rocket as it's going down, because we have the overall total change in time, the total change of the rocket as it's going down is just going to be equal to the change in the total time subtracted from the change in time that it took to go up. So we can rewrite that as the change in time total minus this negative Vy over G, which in that case we can actually just add. So it equals total time plus Vy over G. As long as you make sure that what we're noting is gravity is negative 9.8 meters per second, if we are accounting for all our directions, then we're fine. So now that I have my changes in time, what do I want to do with them, right? I'm going to use them to calculate the changes in height. So the first change in height I'm going to use is I'm going to use the total change in time as the rocket is going up to calculate exactly how high off the top of the roof the rocket went. Because remember, the rocket doesn't start from the ground. So I want to figure out the total height off the top of the roof that the rocket went. So we're going to call this change in y1. And that's going to be equal to 1/2 the change in the velocity, which in this case, from when it's launched, when it goes up. So that's just the 0 minus Vy times the change in time as it's going up. So if we keep doing the math, we get the first change in y being negative 1/2 Vy. And then instead of writing this delta t up, I'm actually going to write what we've calculated for it. So that's the negative Vy over G. So, oh, there should be an equal sign right there. So the first change in height is going to be equal to Vy squared over 2G. Now let's calculate the second height. We're going to actually take a look at it here, as the second height is going to come from the second time frame, so the time it takes for the rocket to go down. Let's call this change in y2. This is the change in y going down, and that's going to be equal to 1/2 a t squared, and this is the t going down. That's important to note. And the acceleration in this case is gravity, so our change in our second height is going to be 1/2 g, and then this time it takes to go down is the change in total time, right? Total time plus this Vy over G, and all of that is squared. And this is going to give us basically when the rocket reaches its maximum height all the way till it hits the ground. That's going to be that total height. And so we want to figure out what is the difference between the two. So when we actually calculate the height of the building, right, the height of the building is going to be the change in y2, right? So the overall height from when it reaches its top minus that change in y1, that height that it took as it traveled above the building. So that difference is going to be the height of the building. So let's plug everything in, and let's actually get our full final algebraic expression before we plug any numbers in, and then we'll calculate it from there. So let's shorten this. We'll just call it delta y, so the change in the height of the building, and that's going to be equal to our delta y2, right? So that was the height that it took the rocket to go from its total top height all the way down. So that is 1/2 g, we'll just say g over 2, times the total change in time minus, instead of writing Vy, let's actually write what Vy is. So that's V times the sine theta over G, and that is squared, and we're going to subtract from it delta y1, right, this change in time, or the change in position, sorry, as the rocket goes to its highest point. So instead of writing Vy1, we're going to write out what it is. So it's V, in this case, squared sine squared theta. I'm just factoring the squares through over 2g. And this is a full final algebraic representation. You could probably simplify it a little bit, but it really actually wouldn't make it much more simple. So in this case, we're just going to plug in values and we're going to start solving it from here. So our building height is going to be negative 9.8 meters per second squared divided by 2 times the total seconds, right? So that's 2.8 seconds. I always like to write all my units because if you've done your algebraic expression right and you apply everything to the units as well, if the units cancel out and you have the right unit left, then you've done it right. So at the end, we should just have meters if we've done this correctly, because all the other units will cancel. So this velocity squared is, or this velocity here is 20 meters per second times the sine of 35 over negative 9.8 meters per second squared. All of that squared minus 20 meters per second squared sine squared of 35 over 2 times negative 9.8 meters per second squared. And if we actually plugged in all the units and did everything, would see all of those will end up canceling. We would be left with, so this one would be over seconds, so that would be a second minus, oh, sorry, there should be a minus sign there, sorry. This should be, it'll be second plus a negative second. You'll end up with the difference, and that'll be squared. That'll take care of this second squared here, and the rest would follow suit when you're subtracting it from here as well. When we plug this into our calculator, though, something you might notice is we get delta y b equals, have something like negative 13.0097 meters minus negative 6.714 meters. And that's okay. This negative, because you're going to get an overall change, is going to be negative 6.2957 meters, thereabouts, depending on the significant figures you used in actual calculation. And it's okay that this is negative. It's not saying our building is in the ground. It's just because it's taking into the direction into account. We were going down, if you think of down as the negative y direction. So all we have to do is just make it an absolute value right there, kind of thing, because the height has kind of an absolute value to it, and that the height of our building is 6 point, and we could just round to the first decimal point, 6.3 meters tall. And this is how you can use parabolic motion to find a number of many useful things regarding kinematics.